Hello everyone. The USACO problem that we're looking at today is actually so old that it's no longer on the USACO website. Because as you guys all know, USACO only keep problems as old as 2011, and this one is actually from USACO 2009. So that's why I'm using a different website called Luogu, which is another online judge that actually keep problems older than USACO does itself. So the problem that we're looking at today is the USACO 2009 February contest Gold problem of revamping trails. And the problem on Luogu is labeled P2939. You can pause the video first and look at the problem statement yourself. I know it's kind of messed up, but it's also very, very old. So basically, I'm going to explain it here for you because I know this is not the usual format. But basically, you're given M roads and M pastures, and you're trying to upgrade K of these M roads so that the time it takes to traverse from node 1 to node n is minimized. So K is at most 20, N is at most 10 to the fourth, and M is at most 5 times 10 to the fourth. And you have a time limit of 2 seconds. And now you can pause the video first and think about this yourself. Alright, I assume you thought about this problem. So basically, the first thing that we want to notice is that K is very, very small. And actually, the reason I'm doing a problem this old is actually because of the algorithm that we're going to be using here. It is very classic, I would say, not very commonly used, but this is probably the best template problem that I can find on this algorithm called layered graph shortest path. And one of the most important characteristics of these types of problem is some value is very small. Like, for example, the K in this problem is very small. It's only 20. And some other problems have maybe, this problem is upgrading roads. Other problems might be like building new roads or stuff like that. And when that value is very small, you might want to start thinking it could be layered graph shortest path. And for this one, how do we use the algorithm? So first of all, notice that K is only 20. And the idea here is to actually construct a graph with 20 layers. So let me show you what I mean by that. So basically, we have a graph of 20 layers. So think of all those like a 2D plane. And each of those layers, let's just think of each graph instead of as 2D as 1D now. So these are all nodes. These are all like points on the graph, right? And all the points are copied on each of the layers. All right. And now we have trails between them. So say we have a trail between point 1 and point 2, point 3 and point 4, point 4 and point 5, and then point 3 and point 1 maybe. No, point 2. How about that? And now these trails are going to be built. We're going to build the exact same trails on every single layer, on all of those layers. Just copying them down. However, we're also going to build a few extra ones in between layers. And this is where things get interesting. We actually build an exact same path except to the second layer. So we have a trail from 1 to 2. So now we build a trail from 1 to 2, but from 1 of layer 0 to 1 of layer 1. Layer 1, layer 2. And the same thing with this trail that went from 2 to 3. Now we go to the 4 of another layer. And same thing with this one. Same thing with this one. And we do the same thing with layer 1 and layer 2. So this is for K is 2 right now. So we do the exact same thing. I'm not going to connect all the edges here, but now you get the idea. So why do this? Well, actually now for the edges that we connected between graphs, we change the weight of these edges into 0. Because we know when we upgrade an edge, the weight of that edge becomes 0, right? And now for the edges that we connected between the layers, we change them into 0. And now if we just simply run a very simple standard digester algorithm using the 1 on layer 0 as the starting point and the n on layer k as the ending point, we actually found the path. We found the length of the path. Why? Because if you think about it, all these edges are directed. We made them to be directed, so we can only go from layer 0 to layer 1 or layer 1 to layer 2, never backwards. We only go to higher layers, never backwards. Which means when we went from layer 0, from point 1 on layer 0 to point n on layer k, we went through exactly k upgraded trails. Because each of those trails that travel between layers are upgraded, right? Because we set the weight of those edges to 0. So we travel exactly k upgraded trails. And that's actually really, really simple now, isn't it? We just connect edges, make a graph, and it's just standard digester. And it's actually pretty easy to understand. So I actually really like this algorithm of layer graph shortest path because it's just so simple. and so easy to understand. If you get the idea, you will know how to solve the problem almost immediately, and the implementation is not hard at all. And also, I'm pretty sure on this problem, you don't have to revamp exactly K. You can revamp less if you want. So that's why I'm in my algorithm. If you reach an end on other layers, you can also compare that to the answer. And if it's smaller than the final answer of the one on the kth layer, obviously we take that as the answer, because that means revamping less trails is even better. But I don't think that will ever happen. So now knowing this algorithm, let's see the implementation. Yeah, as I said, this is a template of layer graph shortest path, and I'm not sure if that's actually an algorithm in America, but this is the Chinese name for that algorithm. Layered graph, that's literally layer graph, and that says shortest path. All right, here's the implementation. I actually stored a num array, meaning the number of, like, what is the title, what is the label of the jth point on the ith layer. So it's easier to to know what that point is labeled, and easier to connect edges. And as you can see, these are edges that run between layers. Now, for each layer, first of all, we connect edges obviously within them, and that's layers that run between them. That's edges that run within them. We connect edges, and then that's just standard digextra, good old digextra, and we output the answer. And it's just that simple. You just connect extra edges, and you're done. It's just digextra, nothing else. Now you see how I love this algorithm so much. It's just so easy to implement and so easy to think of, actually, if you just know this. And the reason that I'm doing this problem, even though it's so old, is because this will help us better do the problem that we actually already did once yesterday, but again using this algorithm now. Because if you remember from the video yesterday I think I reviewed the USACO 2021 January contest gold of telephone. And that problem can also be solved using this similar algorithm. So if you want to just maybe think about that and try to solve it yourself without me posting the video tomorrow, and of course I will still explain how to use this algorithm to solve that one, but that'll be tomorrow. And this problem is just help us understand the basics of this new algorithm. All right, hope this video helped. Thank you for watching. All right, that was a problem review, and here's the grind report today. I didn't actually do much today because I'm still kind of sick, better than yesterday, but I still didn't actually do as much as I would like to. I mocked a gold contest, a pretty difficult one actually. It's the wait, where did the problem go? 2022 January gold. Yeah, and it's way too difficult. I didn't thought it was gonna be that difficult. I solved the drought. I solved half of it on my own, and I was just really, really close to solving all of it. And it took me like 15 minutes after contest, after looking at solution, to completely solve it. So drought, I think I basically almost solved it. If I spent more time on that, I probably could have. And the second keyword is way too hard. Farm updates, I still don't know what algorithm it is. It's like almost like a segment tree except on the graph. I don't know. And then we have the test for hay bales. I don't even know what the problem is really asking me to do. But anyways, I just kind of gave up on the last two and solved the drought, and that's all I did today. No, actually, that's not what I did today. I also solved a problem called the convoluted interviews. No, convoluted intervals. And it's the USACO 2001 December. So let's take a look at that one. This contest, the silver problem, convoluted intervals. I actually solved it a while ago. I think it's 2023 March that I solved it, but I don't remember anything from last time I solved it, which is why I still couldn't solve it even 2 years later now, which is very, very disappointing. But it's an important method because in this problem, you actually learn how to utilize the small range of the values, even though there's a lot of them. And this is a classic trick. That's why in the Google Docs that I organized all my problem in, I put it as green, which is a very high level for problems to review because it's an important technique. All right. Didn't do much today, but that's because I'm sick and I'll actually lock in now. Like, why do I have to get sick on weekends? Weekends are the best days for grinding. Now tomorrow I have school and I'm feeling better. That's just stupid. All right. Thank you so much for watching, and I'll grind more tomorrow.